all the organizers of this wonderful meeting for giving me a chance to tell you about some of our work. I'm in the physics department of this institute, and I hope you have had some time to look around the institute. All right, there we go. This work that I'm going to talk about, some of it is old. It was done by my then student Ganapati Sahu, who is now in the University of Rome, Tor Vergata, and Rubaditto Mitra, who's in Nordita in Stockholm, and some recent work has been done by Soham, who's in the audience here. Okay, and these are the agencies that have very generously funded our work. All right, so here is the old paper. There is some new stuff which I will go over. And there are many related references, all of which I will not be able to cover, but which I might allude to as we go along. In particular, some of our work was motivated by these papers. The lead author is in the audience, so you can ask him all the hard questions. Okay, he didn't realize he has to answer all the hard questions. Okay, there are many studies of dynamo transitions, and I will come back to that as we go along. So here's an outline of my talk. It's quite a short talk, so you don't have to worry. Some introduction and motivations, equations that you know well, another set of equations which some of you probably know well, but all of you might not, so I will go over them in a little bit of detail. And then within this shell model for 3D MHD, I will illustrate how one can study dynamo action in far greater detail than is possible if you, of course, use the full 3D MHD equations. But of course, life is not as simple as a shell model, so I will try to end with some preliminary results for 3D MHD and some concluding remarks. Okay, this picture might have been shown earlier, but in case you haven't seen it, all right, let's see. This is a magnetic Reynolds number, which will be defined presently. This is magnetic Prandtl. And on this scale, the sun is here, and the Reynolds is marked here. These are huge numbers. In case you can't see them, don't worry. Just remember they're pretty huge. Okay, simulations are here. Experiments are here, and these are log scales. That's the galaxy. That's Jupiter. That's the sun. So simulations are very far away from all realizations of the sorts of systems we are talking about. Okay, there's a color version of this figure now in a write-up in Physics Today. Again, Reynolds here, magnetic Reynolds here, simulations here, some overlap with plasma experiments, but most of the other things are far away. I'm sorry? Can you, what should you do with the color?
Brought color to this.
I don't know whether he did or what. I mean, it's in that. I think it's just 2005 versus 2011. I mean, 2005, even you might have been involved in that figure, I think. Or, yeah. Okay. All right. Okay. I normally take a statistical view of turbulence. So I would like to say that the dynamo transition, at least the one that we are studying, is a very good example of a first order phase transition. Now, again, all of you probably know this thing, but in case some of you haven't looked at statistical mechanics for a while, let me recall the most elementary first order transition. This occurs in the Ising ferromagnet, which at temperatures below the Curie temperature, shows ferromagnetic ordering, and let us say there is also a magnetic field. In equilibrium, certainly in 2 dimensions, you can do it in great detail, but even in 3 dimensions, everybody agrees that this is what happens in equilibrium. The order parameter, which is the magnetization, is greater than 0 if H is greater than 0, and less than 0 if H is less than 0. And separating these 2 phases, which are characterized by these positive and negative values of this order parameter, there is first order phase coexistence along the phase boundary at H equal to 0 and T less than Tc. Now, if you go away from equilibrium, which you can do in many different ways, you can observe the following. If you just were in equilibrium and you plotted m versus h for t less than tc, you would see a healthy jump from a positive value to a negative value, and that's the classical equilibrium first order transition. But now if you start cycling this field, positive and negative, you will see a hysteresis loop, which all of you must know from elementary physics. Furthermore, if you quench, that is, you change the sign of the field rapidly, then of course the magnetization must follow. So let's say that you are in a sea of down spins because your H is negative, you suddenly make it positive, M must become positive, and this it does typically by nucleation. You get a nucleus, a droplet, which grows. If you have a very shallow quench, when you are very close to that first order boundary, the nucleation time, the time required for the formation of the critical nucleus, diverges as H goes to 0. Also, if you study this model by Monte Carlo simulations precisely at first order phase coexistence, which is at H equal to 0 and T less than Tc, you see reversals. You will see M up for a long time, then suddenly down. Stays down for a long time, suddenly up, and so on. Okay, so does this remind us of dynamos? Of course, all of you can see that it does. But of course, if you want to study dynamos, you can't do simple Ising models. You must confront these MHD equations, which you must have seen several times in these lectures. I put them up only to establish the notations that I will be using. U is the velocity, B the magnetic field, P is the pressure. That's the combined pressure. You can combine it like this. Nu is the kinematic viscosity, eta is the magnetic diffusivity, and there's the external force. All right? All right, and of course, incompressible and divergenceless, and the dimensionless control parameters now, the Reynolds number, VL over nu, magnetic Reynolds number, magnetic Prandtl, nu over eta. Okay? These are standard length, velocity. Okay. Now, that's too hard, as we will see, as Yannick Ponty and his collaborators showed us. Okay? I will show you the data in a minute. So, if you want to study something in great detail, and I will define what I mean by great detail very soon, it is advantageous to use a shell model. These shell models go back very far. This particular one was, we thought, invented by this former student of mine on this campus. But it turns out, I think Axel had something very similar earlier. Axel Brandenburg had something very similar earlier, and one more, Frick and Sokolov also had something similar. Okay, so what is this? This says that MHD is too hard. So I'm going to replace my vector u by a complex scalar u sub n. Think in a sort of Fourier space. So this is, if you like, the Fourier representation of the viscosity and the magnetic diffusivity. This is like the nonlinear term. And these constants a, n, b, n, c, n, etc. I will give you in a minute. So this is a shell model insofar as we have shells that are labeled by n. These are logarithmically spaced in a Fourier space. So the wave numbers that go with each shell are k naught times, let's say, 2 to the n. And these are the velocity and magnetic fields. Rather, they're Fourier representations, if you like. They're scalars, but complex. And in any calculation, we must keep a finite number of shells. So between 1 and capital N, and we will typically keep n equal to 30. And you can work out the details that if you want to ensure the conservation of the shell model analogs of the ideal 3D MHD invariance, you must choose these values for A, B, C, D, E, F. Okay, this is no free parameters anymore, and the good thing about it is that if you set all b's equal to 0, it will reduce to the well-known Goy shell model for fluid turbulence. Okay? All right, how do we study these? For the full MHD equations, we do a standard pseudospectral method, suitably de-aliased and so on. And for the shell models, what we do is we use an Adams-Bashforth scheme. Schematically, the equations can be written like this, where this includes the nonlinear term. Then the second order Adams-Bashforth scheme is written out like this. And unfortunately, these MHD equations are quite unstable. At least we found them quite unstable. So occasionally we use a fifth order Adams-Bashforth scheme. Okay, these are details. This just tells you that we know how to solve these equations. And now I will tell you what we learned by solving these equations. So as all of you know well, I mean, a dynamo is the amplification of a weak magnetic field in some turbulent conducting fluid because of the stretching of field lines by randomly moving fluid elements. So that's what we would like to do. A shell model is too poor to do this. I mean, the velocity is a scalar, there's no vorticity, you know, but it gives you, what does it give you? I'll tell you what it gives you in a minute. But just to say the general things first. If the magnetic Prandtl number is much greater than 1, then the resistive scale is much smaller than the viscous scale. Did I say that right? Okay, whichever way is the correct way. Okay, then you can get a small scale dynamo, and the other way you get the growth of the magnetic field in the inertial range. And dynamo action is obtained only if R sub n is sufficiently large to overcome the Joule dissipation. So if you have enough computing time like Yannick does, then you generate a figure like this. Okay? Rm on the vertical axis, inverse Prandtl on this axis. And they did this calculation. So down here is no dynamo, upstairs is dynamo. And in spite of all their numerical power, you know, this is a real tour de force. But they couldn't do DNS all the way. To get all the points, especially the ones here, if I'm not mistaken, they use LES and something called LAMHD, Lagrangian averaged MHD, is that correct? Huh? Okay. So these are some fixes. This DNS, I guess, works here. And as you can see, error bars are quite large. And this has taken several years and several millions of hours on the world's leading computers. Okay? But what are you after? You're after this, what I will call a phase boundary. The essential message I am trying to convey to you is that just like in the Ising model, we had a phase transition from a downspin phase to an upspin phase. I can think of dynamo action as a non-equilibrium phase transition from one turbulent, non-equilibrium but statistically steady state, which is a turbulent fluid, to another such non-equilibrium turbulent state where the magnetic field also exists and is also turbulent, right? Okay, so suppose we wanted much more detail for such this phase boundary, and we just cannot do it with the computers available in the world today. Perhaps you can do a little more now because this was done about 10 years ago. If you wanted to explore a wide range of magnetic Prandtl and magnetic Reynolds, and you wanted to study this dynamo onset from the point of view that I just described, then it is advantageous to use the shell model. And when we use the shell model, if we are going to push this analogy with first order phase transitions, it is useful to have an order parameter which plays the role of the magnetization in the Ising model. A natural order parameter here, which has been used, of course, for several decades, is the ratio of the magnetic and kinetic energies. And eventually, what we are after is this stability diagram or non-equilibrium phase diagram, if you like, for dynamo formation in this plane, the inverse Prandtl and REM plane. I will show you that at least as far as our calculations go, this boundary appears to have a fractal character. The order parameter shows hysteretic behavior in the same way that the magnetization shows hysteresis in an Ising model, and there are also suggestions of some nucleation type phenomena. Okay, so these are numbers. We've chosen a small step size, lots of shells. That's the typical diffusion time. That's the large eddy turnover time. So if eta is small, that's a very large time. And I think Yannick and his group, where they found that they had to run very, very long, of times of order this to get dynamos. And so what you want to see is that once the magnetic field saturates, it never decays, barring very small fluctuations. So what we do is we start with a very tiny initial magnetic field. This we can do in a shell model. This is not very easy to do in full MHD. And we say that dynamo action has occurred if this ratio becomes comparable to 0.9. Not always, sometimes, okay. Most of the time 0.9. And we have a tiny initial kinetic energy, some initial kinetic energy. And the time required for the formation of a dynamo is typically much smaller than this diffusive time. Okay, and if that doesn't happen, we show that there is no dynamo action. So this is a plot of the evolution, time evolution of energies. The red is the kinetic energy of the fluid, and this is the magnetic energy dashed blue. And here A, B, C, D, you see a dynamo has formed. And in E and F, no dynamo. So from such runs, we can also ask what happens to the spectra when we do such things. Well, precisely what happens, as you might have guessed, depends on the value of the magnetic Prandtl number. Please note the values of these Prandtl numbers. You would have a tough time doing these Prandtl numbers for full 3D MHD. Okay? But given a shell model, you can do it. And so in this case, you see that first the magnetic energy increases first at large K and then moves up to small k, whereas in the other case, it goes the other way. Did I say it the wrong way? Okay. Anyway, this is the way it does it. Now, of course, the kinetic energy, the velocity is also affected by the buildup of the magnetic field. The initial one is the squares which are up there, and that's the Kolmogorov 5/3 law, and you can see that this is how it is modified as the magnetic field grows. Now let's look at the order parameter. How does it behave? The order parameter, I remind you, I suggested should be the ratio of the magnetic energy to the kinetic energy. In the no dynamo regime, which is shown in this inset, not surprisingly, it goes to 0. Okay, so that's no dynamo. Then as you increase magnetic Reynolds, you get some plot like this. I will let you decide whether you want to call this a dynamo or something in between. I will comment on that later. So that's the green curve. It's oscillating a lot, but at least this is non-zero. It's not exactly 0.9, but it's non-zero, and this is oscillating for a very, very long time. And here is a well-formed dynamo, and that's in the dynamo regime. Okay, so blue dynamo, green intermediate, red no dynamo. From many, many, many such runs, each point on this stability diagram is a run. Okay, this would be completely inconceivable in 3D MHD. Now, this is a complicated plot, so first let me explain to you what it means. The green stars, the crosses down here, are no dynamo. The red ones, the red circles up there are dynamo, healthy dynamo. I've drawn some lines to show you that in between it's very complicated. Very complicated in the following sense, that if I actually go up one of these lines, I will think I've got a dynamo, and then suddenly I'll find no dynamo. The initial conditions are the same for all these runs, but if you want to use the language of, phase transitions, the phase boundary between these two non-equilibrium phases is very, very complicated. It looks like almost like a fractal. Now, does that mean there's a bug in the code, or can that happen? Okay, we've checked and we are sure there's no bug. And indeed, this is observed in many dynamical systems which are nonlinear. It's even observed in transitions in pipe flow. And what happens, of course, one way of rationalizing it, that for the dynamical system, it's a very high dimensional dynamical system. There are two attractors. One is the dynamo attractor, the other is the non-dynamo attractor. Both are presumably strange attractors. And there is a fractal basin boundary separating them for a given set of parameter values. But the moment you change the parameter value, that is, you change REM or you change Prandtl, you've changed your dynamical system. And the same initial condition might give you, dynamo or non-dynamo, depending on which side of that fractal basin boundary it falls. Now, okay, so one of the qualitatively new messages that this boundary can be very, very complicated. Then I promised you some hysteresis like in the Ising model. Well, there is hysteresis here too. So, blue is going up, red is coming down, that's the amplitude of the force. This one is at some rate, that one is at some other rate. This is held constant for 10 time units, this is held constant for 1 time unit, and you can see that you get hysteresis loops. You can also ask, how do you calculate a nucleation? Yes? Yeah. So here you take your forcing term, all right? I make it a function of time, all right? So at sufficiently low forcing, Reynolds would be low, there'd be no dynamo, all right? Then this is like superheating and supercooling in a liquid, okay? When you go through the boiling transition, or you take a crystal and you heat it, you get a liquid, same thing, all right? But it's also well known in statistical mechanics, for example, spin systems, that when you change the rate at which you scan, you change the size and shape of the hysteresis loop. It's precisely what is happening here. Okay, you can do nucleation time by estimating when did I reach my dynamo threshold. Okay, you do that, and roughly you estimate the distance from the dynamo boundary. Now, of course, I showed you it's a very, very complicated boundary, so I can't give you a real number. But at some point, I take some nominal boundary Reynolds number, which is REMB, distance from that, and as you approach it, the time for the formation of dynamo is, well, I won't say diverging, but it's certainly becoming very large, and that's typical of nucleation phenomena at a first order transition. Okay, so let me not dwell on it. I've said all this. So let me just say, well, can we get similar results in 3D MHD? It would be wonderful, but we can't get it in that much detail, of course. We have some preliminary results. So here are some plots. You can't see very well here, but this is a low Reynolds. This is a Prandtl of 1. Low Reynolds, high Reynolds, in between Reynolds. And that blue is the order parameter, EB over EV. Here it goes to 0 eventually. Here it can't make up its mind. It's like that oscillatory one that I showed you. And here it's building up. And this will eventually become a dynamo. We have already run for about 13 large eddy turnover times, so it's still not long enough. But okay, that's the price you pay for doing full 3D MHD. You can try to see if there's something like nucleation. So I will just show you a quick movie of the case where we do have some. So here is the green is the vorticity field, and those little specks of red are some seed magnetic field. And in this case, it will grow. So I will show you how it grows. Okay, so here the nucleus did succeed in giving you a dynamo. There's a cyclic boundary condition, so you'll see it over and over again. I can show you a movie which I won't, which doesn't have a dynamo. So let me just end with some cautionary remarks that look, this is a very complicated dynamical system. I hardly need to tell all of you that. But in some ranges of parameters, a dynamo transition can be continuous, which in the terminology of people who do low dimensional effective models is supercritical as opposed to subcritical. For example, Mahendra Verma's group has studied this in quite great detail in some effective models. Then you might ask, is there only one dynamo boundary or is there a sequence of transitions? For example, you could first go to a state where you have an oscillatory dynamo and then a dynamo that saturates. Already in the morning we heard about different types of dynamos, and I think it would be nice to sort this out even at the level of homogeneous isotropic turbulence, but I don't know whether the time has yet come for that, because to get this much computer time might not be easy. And okay, given that this dynamo boundary separates two turbulent, sorry, this is jargon from statistical mechanics, non-equilibrium statistically steady state. Okay, you might expect that the boundary might depend on precisely how the system is forced, and indeed evidence exists for that. I mean, how the Taylor-Green dynamo works is different from how some other dynamo works, and so on. So with these cautionary remarks, I hope I have convinced you that we can at least get some interesting perspective if you think of dynamos as a first order phase transition, as in statistical mechanics, and I thank you for your attention. Perfect.
Time for questions?
Okay. Yeah.
Yeah, so there's quite a bit of Taylor-Green work and the dynamo work that Emmanuel presented some time back.
Yes.
Yeah, for low Prandtl numbers, there is a subcritical transition.
Yes, right.
For large Prandtl number, there is a supercritical transition.
Right.
And,
So at least in the range which we saw, we didn't see a crossover in this shell
can
model.
you just look at your transition figure?
Yeah, but
Where you had shown the transition, maybe.
yeah, I'm pretty sure that I don't have the data you want, but I'll show it to you. This one?
One after that, one after that.
This one.
Yeah, yeah.
Ah,
So low PA will correspond to large
yeah,
other side.
this side. Yeah, this side somewhere.
So it will be nice to see.
I know. No, okay, we'll go back and do it. Probably young Soham will take that to the challenge and do it. Okay.
Another thing is
Yes.
that for near the transition, okay, you are saying that there is a dynamo state and no dynamo state.
No, but I also gave you a cautionary remark that there might be hundreds of things in
So
between.
the dynamo states could be of different, the dynamo could be different attractors. Even no dynamo could be different attractors. In DNS we see that.
Yes.
So there are multiple ways to get to different attractors.
Absolutely. I will never, I agree. Yes.
When you define the other parameter on TP over PU, so you're saying that when it fluctuates, it's not really a dynamo, or you don't know?
No, look, I mean, again, to give you an example from statistical mechanics, there are things called colloidal crystals. You can shear them. They go into a state where it is not only periodic in space, the crystal, but it's also periodic in time. So there's no problem having an oscillating state. You can have just like you mentioned in the morning.
So we, all the community, we put that a dynamo. The fact that EB over EU is non-zero, so this is a dynamo.
Yeah,
Even if it's fluctuates.
that's fine.
And then, maybe more surprisingly, what happened for above onset? There is no more fluctuation.
Well, it is less. I mean, no, it's not zero. I'll show you. I mean, if I blow it up, you will see fluctuations here. But they're not, I mean, if I were to do a temporal Fourier transform here, I might even fish out a peak. That means there might be some periodic thing. But if I do a temporal Fourier transform here, I don't think, I just get broadband noise.
Yeah. But the solution is still fluctuating, because
Of course.
there are some shell models which, if you increase forcing, the solution becomes steady.
No, this is not steady. No, this is not steady. I forgot to mention that there are shell models where you see that, what's it called? The flipping from, yes, reversals, yes.
And one of the features of the dynamo models from the 3D DNS is that there are different types of dynamo model resulting. Sometimes you get dipolar large scale,
Yes.
sometimes you get multipolar small scale, sometimes you get symmetry. I mean, is there any way you can get to a more than one order parameter in order to actually...
Oh yes, no. In the 3D, of course. In the
anything the shell model results?
no, shell model is too poor to distinguish dynamo.
You can't distinguish different types of dynamo at all.
Well, it might have its own zoo of different dynamos, but they will not cover dipoles and quadrupoles. A shell model is too poor for dipoles and quadrupoles.
They might,
I mean, you might write a richer shell model.
Small scale, you might get solutions where the dominant energy, contribution of the energy is in large scales, and another one where the dominant energy is in small scale.
Yeah, that you could probably do. You could see, but that you change with Prandtl. I mean, whether it's a small scale or large scale. But dipole, quadrupole, I think it's not rich enough.
Yeah. No.
Okay.
Can I ask also a
Sure.
question? Have you looked for on-off intermittency close to the boundary?
No, but you have, right?
Yeah, and I
yeah.
think many of these results could be explained by that, because if you have fluctuations,
Yeah, I've looked at your paper, so I haven't gone back and reanalyzed our data from that point of view. I will do so. Yeah. Okay. Thank you.